Welcome to this introduction of Iter8, the Kubernetes release optimizer. The goal of Iter8 is to ensure that Kubernetes applications and ML models perform well and maximize business value. The general approach to achieving this is to test at all stages of development and operations. Each testing strategy, performance testing, A/B testing, and progressive rollout, all have challenges that may become barriers to adoption. Iter8 provides tools and techniques to reduce these barriers, enabling earlier adoption in development and operations. Let's explore each in turn. The first approach, performance testing, ensures that applications and ML models perform well. The key challenges to adoption are installation and configuration. It's necessary to install and configure load generation to drive tests. Further, it's necessary to install and configure a metric store or database. And finally, some form of visualization will be needed to inspect test results. Iter8 provides built-in load generators, a built-in metrics database, and integration with Grafana for visualization. By providing default built-in components, Iter8 can provide near zero-cost setup for performance testing. The load generators built into Iter8 support testing against one or more HTTP and gRPC endpoints. Before load generation is started, Iter8 can ensure that applications or ML models are ready. When testing is completed, it can send notifications. ABN testing is used to compare the business value of two versions of a system. We explore the challenge of applying ABN testing, in particular to back-end systems, where ML models typically reside. ABN testing involves the evaluation of business metrics. These metrics are computed over a user transaction or user session. A user session typically spans several user interactions. For example, in an online store, a user may explore several products before finally making a purchase. A business metric would be computed over the whole sequence of user interactions. Necessarily, the metric is computed by the user-facing or front-end component because it is aware of the whole session. Front-end components typically are not guaranteed to interact with the same version of a back-end system throughout the entire user session. Even when such a guarantee is provided, the front-end component does not typically know which version of the back-end component is used. This is hidden by the routing configuration. As a consequence, the front-end system is unable to associate the business metrics that it computes with a particular version of the back-end, making it impossible to do effective ABN testing of the back-end component. To address this challenge, Iter8 provides a very simple SDK that can be used to implement the front-end component. It provides a routing API lookup that identifies a back-end version that should be used for interactions. The routing API guarantees to return the same back-end version for the same user session. This allows a front-end component to know that it is communicating with the same version of the back-end component, and therefore to associate a business metric with this version. In addition to the routing API, there's a metrics collection API, write metric, that enables the front-end component to write business metrics associated with the appropriate version of the back-end. This Iter8 SDK is supported in multiple languages. Its implementation is based on gRPC. Further, the Iter8 SDK builds on the capabilities provided by performance testing, the built-in metrics database, and it extends the Grafana integration. When we say that Iter8 provides a simple SDK, what do we mean? Here's what it looks like for a front-end component implemented in Node.js. Calls to the routing API lookup take a reference to the back end and to the user session and return a version number, the same version number for the same user session. This is used to look up a route which is then used to make calls to the back end. The metrics collection API write metric is then used when the user session is complete to write any computed metrics to the metrics database. Finally, let's explore progressive release. Progressive release is a technique in which, after we deploy a candidate version, the traffic is rerouted so that some portion of it goes to the candidate version. Traffic can be routed based on a percentage, as in blue-green routing, or based on the request itself using perhaps the header or a cookie, as in canary rollout. After some time, when we can evaluate the candidate version, we then choose to either promote or delete the candidate, at which time the traffic will need to be reconfigured again. The challenge to adoption is this need to reconfigure the routing each time a candidate version is deployed, promoted, or deleted. Traffic configuration is highly dependent on the ingress or service mesh technology used. Further, it may depend on the type of the application resources that make up the application. How does Iter8 reduce the challenge of reconfiguration? It brings an ability to detect new versions, identify them when they're ready, and to automatically trigger the routing reconfiguration. Iter8 uses a non-programmable approach that does not depend on changes to the Iter8 controller to add support for additional ingress or service mesh technologies. This approach is based on Helm charts. The Iter8 Helm chart defines how the routing should be reconfigured. The Iter8 controller then identifies when changes occurred and triggers the reconfiguration. Users can describe a whole rollout as input to the Helm chart. For example, here's a Helm chart describing a blue-green rollout of two versions. One is the existing version, the second is a candidate version. This rollout is implemented in an Istio environment. In this example, the specification of the two versions is very simple, just some labels and an image. The specification, the full deployment specification, could have been specified. The default Helm chart that Iter8 provides supports routing reconfiguration via the Kubernetes Gateway API, allowing native support for many ingress and service mesh technologies. Further environments can be supported by extending the Helm chart. Looking to the future, Iter8 is planning better support for large language model-based applications. In particular, testing can be used to drive techniques like hyperparameter tuning to improve models. Secondly, two metrics that are relevant to ML models are data and concept drift. We would like to incorporate better support for these directly. Integration with Kubernetes-centric MLOps systems such as Open Data Hub will enhance adoption in this space as well. Flagger and Argo rollouts. Flagger, a subproject of Flux, and Argo rollouts is a subproject of Argo CD. They both have similarities to Iter8. Both support progressive rollouts with traffic splitting, session affinity, and mirroring on a variety of ingress and service mesh technologies. And both provide support for built-in load generation. In addition to these features, Iter8 supports progressive rollout with any CRD or Kubernetes resource type. For example, applications can be composed of Knative services, Kserve inference services, Selden deployments, and can be specified using a litmus chaos experiment. It's possible to extend the CRD support in Iter8 by modifying the Iter8 Helm charts. No programming is necessary. In addition to progressive rollout, Iter8 supports ABN testing of backend components, such as ML models, with business metrics supported by the testing of multiple versions simultaneously, a simple metrics collection and routing SDK, and configurable zero downtime checks. Finally, the Iter8 controller does not require CRD installation. It can be installed by a non-admin actor with namespace scope permissions. This reduces the requirements for adoption and experimentation. Thank you.